Okay, good morning, everyone. It's my pleasure to kick off today's first session of BEAM 2023. So I'm going to give a short introduction about additive manufacturing research. So generally, I'll just talk about a couple of themes. We know that with additive manufacturing, we now have access to a wide variety of complex shapes. Indeed, there are a lot of examples out there that are using this functionality or this possibility to create strong and efficient structures using less material. And also, given today's climate, it's becoming more and more relevant to use bio-based materials and to use natural materials such as soil and earth in order to help mitigate the climate crisis. And increasingly, we're seeing more and more research that is controlling, adding advanced functions into materials, such as controlling its shape by arranging the materials at a mesoscale. So here, this is, yeah. So here you can see that the 4D printed parts are able to autonomously change shape on their own. So interestingly, I think we see a lot of this actually in nature. So we see a lot of examples of natural materials that have this differentiated structure. They're also based out of natural materials such as wood, other biopolymers, and they're able to autonomously change shape, react to the environment to perform a variety of very complex tasks, such as seed dispersal. And I'll just give a short introduction about my research. So I'm Tiffany Cheng. I didn't say it earlier, but I'm a research associate at the Institute for Computational Design and Construction at University of Stuttgart. And so what we are mostly doing is trying to strive for this integrated material, structure, and function that we see in nature into our engineered systems. So what we do is we use bio-based materials, either we co-engineer them or use off-the-shelf materials. We arrange them in bio-inspired structures. The pine cone, as we saw earlier, is a very big inspiration that we often use, and we are mostly looking at programming a responsive function to allow these structures to autonomously react to changes in humidity. So, for example, closing when dry and opening when humid and wet. So we've investigated this theme at various scales. So we have done this a lot at the desktop hobbyist 3D printing scale. A lot of these functions that you see, this movement can only be achieved by these intricate structures, which we are able to create through an integrated combination of computational design and digital additive manufacturing. We also explore this at large scale, so on robotic additive manufacturing scale, so structures from 3 meters to 12 meters in length through our facilities, using the additively manufactured structures and patterns in order to create new functions such as controlled Gaussian curvatures, controlled curvature from double to negative to zero Gaussian curvature as well. And so now I'll give an example of how this can be applied to the built environment, to architecture. So this is a recent project that we did, which really shows this integration from materials to structure to function. So this is a project that is currently on the University of Freiburg campus. And what we did is we co-engineered our own materials. So here we are using cellulose, which is the material that we find in wood. But we mix it into a polymer so that we can actually 3D print with it. We also developed our own computational fabrication tools in order to develop a workflow so that we can apply this material with its unique properties to bio-inspired functional structures that we can control the bending curvature, the direction of bending, and the orientation of bending. And through this, we can create very fast reacting material systems. So here is a 40 printed aperture, which is actually very sensitive to humidity because of the cellulose content that we created. And as you can see here, it's even oscillating with the slight, I guess, the humidity chamber didn't quite regulate the interior microclimate as well, and it's so fast that it can even catch up with these little fluctuations. So what do we do with this? We sought to then apply this to a building facade and use the cell shaping mechanism or the 40 printed mechanism to respond to the weather and to block the sun when it's very hot and dry, and during the winter when it's very, very cold and humid, to actually open and let in the free heating from the sun in order to create a comfortable space, a comfortable climate within the building. So this is just an example to show that because as buildings account for a very big chunk of the emissions, the global emissions globally, it's of critical importance to reduce the energy we're using for heating and cooling in order to help mitigate the climate crisis. And so what I show here, and what you will also see in the following presentations, is how additive manufacturing can be used in the different areas of material, structure, and function in order to solve a lot of these pressing challenges that we're facing globally. So